All right, so let's go over a couple pages. We'll go over some definitions, go through this page and the next page, and we'll get rolling. Okay, so if you've done the vocabulary already, this is going to be a piece of cake. So let's start with the very top. Mechanical waves. So the definition of a mechanical wave is a wave that is an oscillation of matter. An oscillation means like movement back and forth. So it's a wave that moves through matter and therefore requires a medium, which means something to travel through. So for instance, the medium right now is air that I'm talking through. Underwater, the medium would be water, and then this table, the medium could be, I guess plastic or whatever. So so that kind of wave sort of looks like, if you want to visualize it, maybe think of like dropping something in water and then seeing the ripple outward. Notice that's an oscillation of matter. In that case, the matter would be the water, and the movement you can actually see is that circular wave that moves kind of out from the center. So with that being said, we know what mechanical waves are. They would be B, requires a medium to travel through. Awesome. So let's look at the next one, longitudinal waves. This one is also not very difficult. I'm going to pull a picture up and it's going to be a piece of cake, but longitudinal wave is a wave that the motion sort of goes the same direction as, the energy, right? So let me pull this picture up and we'll see it a little bit better. So if we look at this, there's oscillation. This picture here, longitudinal versus transverse. Slinky demonstrates both of them. So a longitudinal wave would be like if you move the slinky back and forth. So forward, backward, forward, backward. You can see the compression of the wave, and it's going the same direction as the energy transfer, right? So in that case, the medium and the energy move in the same direction. So if you're looking back at your unit, I'm going to keep this picture up. You will see that it's D. Okay? So again, on this picture, you can see that the compression moves, and you probably will have done a lab like this previously where you have a slinky and you kind of mess with it. The wave, the compression moves the same direction the energy is transferred. Now, the opposite of that would be a transverse wave. A transverse wave is the one on the right in this picture, and that's where the energy, the wave is perpendicular to the energy. Or the energy travels perpendicular to the medium, right? So in other words, simplifying it, the wave moves up and down, whereas the energy transport is to the right in that case. So that's a transverse wave, right? So easy to see the difference. Longitudinal goes the same direction, everything's the same direction. Transverse, there's a perpendicular in the direction. Perpendicular just means kind of like 90 degrees to the original. So, the third one, I know they're not marked, but it is A. And that it just leaves one more. Electromagnetic wave is the vibration of an electrical charge. And that's something you've seen, the picture 100 million times. So that is C. Awesome. So, you guys have that. So let's go back to the page. So mine looks a little bit different in my packet off to the side that you can't see, but this is what you got. So this is your general picture of electromagnetic radiation from the left, which is the highest frequency in this case, to the right, which is the lowest frequency. Usually on packets and things like that or pictures, it's flipped where radio's on the left, but it doesn't really matter as long as the frequency is matched up with the wave. Something to note, the higher frequency, the higher energy, which also, so high frequency equals high energy. Also to note, short wavelength, this is like the wavelength, it's kind of a weird symbol, equals high energy, right? And then vice versa, low frequency equals low energy. So that's a direct relationship, right? They're the same. And high wavelength equals low energy. So that's an indirect relationship, right? All right, so let's look at the bottom. Wavelength and frequency are directly or indirectly related. So wavelength and frequency are inversely, I guess I said it backwards. They're inversely related. And frequency and energy are directly related. In other words, high frequency, high energy, low frequency, low energy. So hopefully you guys get that. Look in the fill in the blank. The speed of light equals. This is on your formula chart. It's on the last page, and it'll say constant because it is a constant. Generally, when we use it in a formula, we'll round it just to make it a nice clean number. So it is 3 times 10 to the 8th meters per second. So that is the speed of light, right? Really fast, right? You know, when you turn on a flashlight, if your brain could, speed up to that speed, you could actually see the light shooting out of the flashlight and hitting the wall. But we can't because it's too fast. We can't see that. But alas, it is not instant. So let's go to the next page. So remember, this is our formula. This is the formula for the C is the speed of light, right? Remember, C is a constant, which is what we just said. It's 3 times 10 to the 8 meters per second. So C is always 3 times 10 to the 8 meters per second. So this is a formula where we always have one, and we just need to find one or the other. This is the wavelength, that symbol I was talking about, and then this is the frequency. So that's good. Let's get going. Number 1. Laser pointers are a symbol of status among scientists, teachers, and lecturers, while red pointers are more common, green pointers are cooler. Cool. I think that means like neater is what they're going for. Use the wave equation to calculate the frequency of red light with a wavelength of 650 nanometers. And yes, you need to convert to meters. You guys should know this by now. You've done, many of these units. You want to use meters. That's the standard. Okay, so let's do what we always do in these is we put what we have off to the left. This speed of light's here, so I'm not going to put this to the left of each of these because we know it's constant, right? So first thing we need to do is we need to convert this nanometers to meters. Fortunately for us, they tell us, hey, nano means times 10 to the 9, right? So we'll keep that in scientific notation just to be easier so we don't have to write a big number. So they already told us the wavelength, right? 650 nanometers. So wavelength, we're going to get used to just drawing that symbol, just like this, equals 650 times 10 to the minus 9. That means it's very small, right? Because that means move the decimal 9 places to the left. If you want to, what you could do is you could say 1, 2, 3, and then add 6 zeros. So 0.1, 2, 3, 4, 5, 6, 6, 5. So these are the same thing. That's way too bright. There we go. These are the same thing, okay? But I'm just going to keep it in this because I find that simpler. We don't have to convert. So what is it asking for? Calculate the frequency, right? So really, it has to be the wavelength or frequency because we always have speed of light, right? So that's a given. So what we're going to do is we're going to put our formula, C equals the wavelength times the frequency. Okay? Now let's plug in what we know. 3 times 10 to the 8th. You could say 3.0 if you want to do that. That's fine. Equals, remember, they give us the wavelength. So 650 times 10 to the minus 9 times the frequency. And that's it. This is like, these next several problems, this is as easy as it gets, right? I mean, it's more or less like 10 equals 5f. What do? You divide it over, I mean, that's all you're going to do with these. Very, very easy, okay? So what you're going to do, again, divide this out. 650 times 10 to the minus 9. Cancel. 650 times 10 to the minus 9, and you should get a frequency of 5.77 times 10 to the 14. And the frequency is in hertz, just FYI. So very easy. These next ones, again, very, very, very easy. So let's look at B. B says, use the wavelength equation to calculate the frequency of green light with a wavelength of 520 nanometers. So now we're going to figure out the green light. So I'm just going to box this green light, and we have the wavelength of 520 times 10 to the minus 9, just like it said. I'm keeping it in this. I'm not going to write the other form, and I already know C. So let's just straight up write it. So speed of light equals wavelength times frequency, 3.0 times 10 to the 8th equals 520 times 10 to the minus 9 times the frequency, divided out, hopefully I don't make any mistakes, and you should get frequency equals 5.77 times 10 to the 14 hertz. That is a 14. Cool. So, of course, they're going to ask us something to compare. Ooh, I messed up. Okay, my bad. I'm sorry. This messed up. I was looking at the wrong one. Because I kind of like go through these. I don't want to take the time to do the math, so I just look at the key for the answer after I do it. So, hopefully you guys didn't get that, or you probably saw something anyways. Should be 4.62 times 10 to the 14 hertz. If I mess this up again, let me know. It's a simple problem, so really you guys are going to be like, oh yeah, you messed that up. But yeah, something like that, 4.62 or so times 10 to the 14. Okay, so now the question is, which laser pointer is more powerful? Well, remember, what did we say? More frequency, higher frequency, more power. So that one's pretty easy. That is green. Because the green one had a higher frequency, right? So there you go. Okay, so let's do number 2. If you guys want to read all this, pause it and read it. I'm not going to do it because this is like too easy. It's a lot of cool stuff, I'm sure. Ain't going to do it. So, what is its wavelength? Okay, so C equals wavelength times F. We already know C is 3 times 10 to the 8th meters per second. Apparently we know frequency this time, which is 780 times 10 to the 12th. What we don't know is wavelength. Bam, bam. Well, it doesn't matter which one's which. We do the same thing. We divide it out. 780 times 10 to the 12. 780 times 10 to the 12th. So, hopefully I don't mess this one up. Wavelength equals 3.8 times 10 to the minus 7. So there you go. Piece of cake. All these are pretty straightforward, pretty simple. I'm trying to decide if I want to do the next two or not. They're just so easy that it doesn't really matter. Okay. This is what I'm going to do for the next two. You should get one of these answers for each of these. I'm just going to write down 2 answers, and if you get it, you know you did it right. Frequency equals 5.08 times 10 to the 14. Frequency equals 6.82 times 10 to the 14. Keep in mind, yeah, I know when you get 3, you automatically know what 4 is. I need to see the work because that's really the main thing that's important in physics is the work. So make sure you guys write the work, figure it out. Hopefully you guys get the right answer. Confirm it yourself. And that's it. So there you go. That's those pages. So that's it. If you guys have any questions, let me know.